Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. I have prepared a training course on distillation system, which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to review the history of the distillation process, describe the principles of distillation, describe the relationship between the boiling point of a hydrocarbon and pressure, temperature, flow, composition, and level. Describe the various concepts associated with pressure in a distillation system: vapor pressure, partial pressure, relative volatility, compressibility, liquid pressure, and vacuum. Identify the different equipment systems used to make up a distillation system. Explain how the methods of heat transfer apply to the distillation process. Explain the basic components of a plate column. Explain the basic components of a packed column. Contrast preheaters and condensers. Describe the basic principles associated with column design. Before starting the course, let us have a look at key terms. Azeotropic mixture is a mixture of two or more components that boil at similar temperatures and at a certain concentration. The liquid and vapor concentrations of an azeotrope are equal. Binary mixture contains two or more components. Boiling point is the temperature at which a liquid turns to vapor. Boiling range is the range of temperatures from when the lightest component boils, initial boiling point, to when the heaviest component boils, final boiling point. Boil-up rate is the balance of the products, vapor and liquid, returned to the column from the kettle reboiler. Bottoms product is residue. The heavier components of the distillation process fall to the bottom of the tower and are removed. Bubble cap tray is a fixed cylindrical tube, riser, and cap mounted vertically to a horizontal tray designed to enhance vapor-liquid contact in a plate column. Bubble point is the temperature at which a liquid mixture begins to boil and produce vapor. Bubble point curve is the lower curve on a vapor-liquid equilibrium curve and identifies the specific temperature where the mixture first produces vapor. Column loading is the amount of material fed continuously into a distillation column. Cryogenic distillation is often used to separate oxygen and nitrogen from our atmosphere by using low-temperature drying and distillation methods. Dew point is the temperature at which a mixture produces the first drop of liquid on a vapor-liquid equilibrium curve. Dew point curve is the upper curve on a vapor-liquid equilibrium curve and is defined as the temperature where the first drop of liquid forms. Distillate is the condensate taken from a distillation column. Distillation is the separation of components in a mixture by their boiling points. Downcomers are downspouts that allow liquid to drop down to lower trays in a column. Downcomer flooding occurs when the liquid flow rate in the tower is so great that liquid backs up in the downcomer and overflows to the upper tray. Liquid accumulates in the tower, differential pressure increases, and product separation is reduced. Entrainment is the upward movement of high velocity, large vapor droplets in a distillation column. Feed distributor is a device used in a packed distillation column to evenly distribute the liquid feed. Feed tray is a point of entry of process fluid in a distillation column under the feed line. Final boiling point is the temperature at which the heaviest component boils. Foaming is often the result of too much heat, impurities in the feed, or active turbulence on the trays above undersized downcomers. Fractional distillation is separation of two or more components through distillation. Heat balance is the principle that heat in equals heat out. Initial boiling point is often described as the temperature where the mixture first starts to boil or evolve vapors. Jet flooding occurs when the vapor velocity is so high that liquid downflow in the tower is restricted. Liquid accumulates in the tower, differential pressure increases, and product separation is reduced. Local flooding is excessive liquid flowing down a column blocks vapor flow up the column in one section. Material balance is a principle that the sum of the products leaving equals the feed entering the distillation column. McCabe-Thiele is the simplest method used in the analysis of binary distillation. The composition of the mixture on each theoretical tray can be determined by the mole fraction of one of the components. Overall flooding is local flooding expands to entire column. Overhead product is the lighter components in a distillation column, which rise through the column and go out the overhead line, where they are condensed. Overlap is incomplete separation of a mixture. Overloading is operating a column at maximum conditions. Packed tower is a tower that is filled with specialized packing material instead of trays. Partial pressures is the amount of pressure per volume exerted by the various fractions in a mixture of gases. Puking occurs when the vapor is so great that it forces liquid up the column or out the overhead line. Rectification is the separation of different substances from a solution by use of a fractionating tower. Rectifying section is the upper section of a distillation column, above the feed line, where the higher concentration of lighter molecules is located. Reflux is condensed distillation column product that is pumped back to increase product purity and control temperature. Reflux ratio is the amount of reflux returned to the tower divided by the amount of overhead product sent to storage. For example, 120 GPM reflux divided by 60 GPM overhead to product tank equals 2:1 reflux ratio. Relative volatility is the characteristics associated with a liquid's tendency to change state or vaporize inside a distillation system. Sieve tray is a flat, thin plate with small holes in it mounted on a horizontal tray designed to enhance vapor-liquid contact in a plate column. Stripping section is the section of a distillation column below the feed line, where heavier components are located. Temperature gradient is the progressively rising temperatures from the bottom of a distillation column to the top. Ternary mixture has three components. Total reflux is a process where the feed to the column is stopped and the total amount leaving the column from the top, sides, or bottom is returned to the column. Tray columns are devices located on a tray in a column that allow vapors to come into contact with condensed liquids. Three basic designs are bubble cap, sieve, and valve. Tray drying occurs due to low feed rates, low reflux rates, or high upward vapor flow rates from tray to tray. Vacuum distillation is the process of vaporizing liquids at temperatures lower than their boiling point by reducing pressure. Valve tray is a small round metal disc with 3 or 4 legs called risers that allow the valve to lift as hot vapors push through the horizontal tray. Designed to enhance vapor-liquid contact in a plate column. Vapor-liquid equilibrium diagram is used to help a technician understand phase behavior of a two-component mixture. Vapor pressure is the outward force exerted by the molecules suspended in vapor state above a liquid at a given temperature, when the rate of liquefaction is equal to the rate of vaporization, equilibrium. Weeping occurs when the vapor velocity is too low to prevent liquid from flowing through the holes in the tray instead of across the tray. Differential pressure is reduced, and product separation is reduced. Overview of distillation systems. Petroleum compounds are composed of hydrocarbon molecules of varying sizes and shapes. Molecular weight determines how a chemical reacts during separation. For example, ethane has 2 carbon atoms and butane has 4. During separation, butane remains in the lower section and ethane moves up the tower. The smallest or lightest components in a tower have the lowest boiling points. A distillation column is built on the principle that light and heavy molecules have different boiling points. Industry relies heavily upon this process to produce many of the chemicals we use today. For example, crude oil is a mixture of many of the chemicals used in modern manufacturing, including straight-run gasoline, naphtha, gas oil, various gases, salt, water, and clay. By knowing the temperature at which a chemical vaporizes, an operator can identify these specific components after they are heated, vaporized, and condensed on the different trays in a distillation column. Distillation involves boiling liquids and condensing the vapors. When water boils, it turns into water vapor. The condensed water vapor is purer than the original mixture because most of the salts, minerals, and impurities do not vaporize at 212 degrees Fahrenheit or 100 degrees Celsius, the boiling point of water. Distillation is a process that separates a substance from a mixture by its boiling point. This simple definition, however, does not explain the complex equipment arrangements that make up a distillation system as shown in picture. The distillation process includes a feed system, a preheat system, the distillation column, the overhead system, and the bottom system. The term system is frequently used to describe the various equipment arrangements associated with distillation. The feed system is designed to safely store, blend, and transport the raw feedstock. This simple system is composed of tanks, pipes, valves, instrumentation, and pumps. Preheating systems are designed to raise the temperature of the raw feedstock before it enters the distillation column. Various heat transfer devices are available for the process. Typically, a heat exchanger or a furnace system is used. Feed rates into and out of this system are carefully controlled. The distillation column can be a packed or plate-type column. Plate columns have a series of trays stacked on top of each other. Packed columns are filled with packing material to enhance vapor-liquid contact. The function of each of these column types is to allow lighter components to rise up the column while heavier components drop down, or, in other words, to separate the various components in the mixture by their boiling points. A variety of arrangements is available on the distillation column to condense the hot vapors and collect and separate the distillate. The bottom system is composed of a section in the column designed to allow liquids to boil and roll freely. A reboiler is connected to this section to maintain and add heat energy into the liquid. The term reboil indicates that the liquid was originally boiling. Hot vapors are returned from the reboiler to the bottom of the column, below the bottom tray. A level control loop is used to keep the liquid at a predetermined level. In the bottom system, liquid level, temperature, and composition are carefully controlled. The overhead system is used to cool off the hot overhead vapors. The condensed liquid is used as reflux or is transported to the tank farm as product. Reflux is returned to the top of the column to control product purity and tower temperature. In packed columns, a liquid feed distributor is used to evenly disperse the liquid. In a plate column, the reflux is pumped to the upper tray. Plate columns are not as sensitive to liquid feed distribution as packed columns are. During the distillation process, a mixture is heated until it vaporizes, then is recondensed on the trays or at various stages of the column where it is drawn off and collected in a variety of overhead, side stream, and bottom receivers. The condensate is referred to as the distillate. The liquid that does not vaporize in a column is called the residue. During tower operation, raw materials are pumped to a feed tank and mixed thoroughly. Mixing usually is accomplished with a pump-around loop or a mixer. This mixture is pumped to a feed preheater or furnace, where the temperature of the fluid mixture is brought up to operating conditions. Preheaters are usually shell and tube heat exchangers or fired furnaces. This fluid enters the feed tray or section in the tower. Part of the mixture vaporizes as it enters the column, while the rest begins to drop into the lower sections of the tower. A distillation column is a tower with a series of trays or packing that provides contact points for the vapor and liquid. As vaporization occurs, the lighter components of the mixture move up the tower and are distributed on the various trays. The lightest component goes out the top of the tower in a vapor state and is passed over the cooling coils of a shell and tube condenser. As the hot vapor comes into contact with the coils, it condenses and is collected in the overhead accumulator. Part of this product is sent to storage while the rest is returned to the tower as reflux. A reboiler maintains the energy balance on the distillation column. Reboilers take suction off the bottom of the tower. The liquid in the tower is circulated through the reboiler. Vaporization occurs in the reboiler and these vapors rise up through the tower. Boil-up rate is defined as the balance of the product's vapor and liquid returned to the column from the kettle reboiler. History of distillation. With the advent of the automobile came a technological boom that affected many existing industries and created new ones. The steel and metal fabrication and manufacturing, glass, machining, rubber, petroleum, concrete and stone industries, and many others had to develop new technology to support the growing automobile industry. As the need for petroleum products grew, more efficient ways for producing oil and gas products were developed. The distillation process traces its roots through three distinct operations: batch, continuous batch, and modern fractional distillation. Batch distillation, as shown in picture, is the oldest distillation process. The raw materials were mixed together and charged to the still. During phase 1 of the distillation process, heat was added to bring the mixture to a boil. The overhead vapors were condensed and stored as final product. At the conclusion of phase 1, the overhead line was switched to a new receiver, and the temperature was increased. When the receiver was full, the process was repeated, and the heat was increased incrementally until the batch run was complete. Product quality during batch distillation operations was very poor. Frequent receiver changes wasted time and money. Continuous batch distillation, as shown in picture, is a continuation of the batch distillation process. A series of stills are connected to each other to form a battery. The temperature of the first still is lower than the temperatures in the rest of the bank. Feed is fed to the first still at a constant rate. Temperature is increased from one still to the next, producing the same effect as batch operation. The stills are connected to each other through the bottom lines. Product quality from still to still is relatively consistent. Modern fractional distillation, as shown in picture, uses a series of trays or packing inside a tower. A continuous feed is heated and fed to the distillation column. Hot vapors rise in the column while liquids drop down the tower. A series of steps involving vaporization and condensation take place inside the column. Vapor-liquid contact allows the heavier molecules to drop out and the small, lighter molecules to rise up the column. The various fractions are separated by their individual boiling points and distributed on the trays. Product purification is enhanced by the still-upon-still approach, as shown in picture. Principles of distillation. The separation of components in a distillation column is based on the differences in volatility or boiling point. As the vapor rises up the tower and contacts the liquid, the concentration of the lower boiling or more volatile components increase. As the liquid descends the tower, the concentration of the higher boiling or less volatile components increases. Increased pressure will result in increased temperatures in the tower. Each section in a trayed or packed column will have its own individual footprint or characteristics: pressure, temperature, composition, velocity, and performance. In the chemical processing industry, distillation and reactor technology are considered to be the two most complex operating areas. The basic principles of distillation include the study of phase behavior of a binary or two-component mixture, bubble point, dew point, boiling range, initial and final boiling points, IBP and FBP, mole fraction, the McCabe-Thiele method, and the concepts of entrainment, foaming, and weeping. Each of these areas is important for a technician to understand in order to work in and operate a distillation system. This picture is often referred to as vapor-liquid equilibrium (VLE) diagram or phase diagram. It provides a simple way for a technician to visualize the complex phase behaviors associated with distillation, boiling, and condensing of a two or more component mixture. In this example, 40% butane, C4, and 60% pentane, C5, will be used. The operating pressure will be controlled at 100 psig. The diagram can be used to show that the mole fraction of butane is 0.4 or 40%. The starting mole fraction of pentane is 0.6 or 60%. This vapor-liquid equilibrium diagram is set up with the temperature on the left vertical axis and the mole fraction going across the bottom. The phase diagram also shows the bubble point curve and the dew point curve. It is important to remember that the bubble point is defined as the specific temperature where the mixture first produces vapor. The dew point is defined as the temperature where the first drop of liquid forms. Looking at the curve, we see that the bubble point for our mixture is 196 degrees Fahrenheit at 100 psig. If we had a mixture that included a butane mole fraction of 0.6, or 60% and 40% for the pentane, the bubble point would be 180 degrees Fahrenheit. We can also see that a 0.4 butane mole fraction would have a dew point of 214 degrees Fahrenheit. As this mixture of butane and pentane heats up, vaporization begins to occur. As more of the lighter component, butane, begins to boil off, a lower concentration of butane will remain until eventually all of the butane will be separated from the pentane. As this process occurs, the bubble point will be shifted for the butane to the left on the phase diagram. It is also important to point out that everything below the bubble point curve will be in the liquid state, while everything above the dew point curve will be in the vapor phase. The McCabe-Thiele approach is the simplest method used in the analysis of binary distillation. The VLE curve just described provides the foundation for a McCabe-Thiele diagram. The composition of the mixture on each theoretical tray can be determined by the mole fraction of one of the components, typically the lightest and most volatile. This method is based on the assumption that there is a constant molar overflow that requires the following. For each mole vaporized, 1 mole is condensed. Molar heats of vaporization of feed composition are equal. Heat effect of solution is negligible. A typical McCabe-Thiele diagram will show the mole fraction of the lighter component in liquid phase on the horizontal or x-axis, while the vertical y-axis will show the same mole fraction of the lighter component in vapor phase. Using this approach, a technician can correctly size a distillation column. This includes the number of theoretical trays in the stripping section, the feed tray, and the number of trays needed for the desired separation in the enriching or rectifying section. Operating lines can be used to define mass balance relationships between the vapor and liquid phases of the distillation tower. Typically, there is an operating line for the rectification or desired overhead composition, bottom stripping section or desired composition, and feed composition. This picture is a simplified example of a McCabe-Thiele model. To construct the operating line for the enriching or rectifying section, the engineering target for the overhead purity is located on the VLE diagram and a vertical line that intercepts the plot point is drawn. The slope R/R+1 is sketched from the intersection point. R is equal the ratio of reflux flow. L is distillate flow. D is the reflux ratio. The calculation for identifying the operating line for the lower stripping section utilizes the mole fraction of the desired bottoms composition. A vertical line is drawn through the target and a line of slope LS/versus is sketched. LS is the liquid rate down the lower stripping section. Versus is the vapor rate up the stripping section. McCabe-Thiele assumes that the vapor above and the liquid resting on the tray are in a state of equilibrium. Another important feature of McCabe-Thiele is the feed line where the binary mixture should be introduced. The condition of the feed is calculated by the slope of the feed line or Q line. In determining overall column design, the McCabe-Thiele approach can help in identifying the required number of stages, degree of separation, and location of the feed tray. Other important factors include tray spacing, internal configuration, diameter, preheat, reboil, and cooling. Another important concept that can be applied to this section is the contrast between the initial boiling point, IBP, and the final boiling point, FBP. Typically, in a multi-component mixture, there is no single boiling point that can be used to vaporize the entire solution. In this example, a boiling range would be needed that would take into account each of the components. This would also include the pressure on the system. The initial boiling point is often described as the temperature where the mixture first starts to boil or evolve vapors. As the mixture continues to boil, vaporization occurs, and the lighter components begin to boil off. As this process continues, the composition of the remaining mixture will become heavier. In order to boil this material, the temperature will need to be adjusted upward. The final boiling point occurs when the heaviest component boils and this temperature is recorded. In many cases, it is difficult to get a complete, 100% separation of components without additional processing. Plate and packed columns used in series may provide this additional processing. When a mixture is preheated and pumped to a 10, 15 or 30 tray column, the lighter components will move up the column as vapor and the heavier liquid will move down and collect in the bottom section. A different molecular structure can be found on each tray, in the bottom of the column, and in the overhead accumulator. The initial feed temperature is carefully controlled as the product enters the column, for example 180 degrees Fahrenheit. Typically, a higher temperature exists and is controlled at the bottom of the column than at the top, giving the tower a unique temperature gradient, for example, 160 degrees Fahrenheit top temperature, 222 degrees Fahrenheit bottom temperature. The top of the column's temperature and purity control is directed at the lighter component and takes into consideration the initial boiling point of the mixture and the specific boiling point of the overhead product. This picture clearly illustrates the basic components of a 15-tray distillation column. This picture shows a packed distillation column and the various internal components. 2 distillation examples. Ethanol and water distillation. A mixture of 50% water and 50% ethanol can be separated through distillation. Ethanol boils at 172 degrees Fahrenheit 78 degrees Celsius, and water boils at 212 degrees Fahrenheit 100 degrees Celsius. As the mixture is heated, ethanol vaporizes faster than water. If the overhead vapors were analyzed, ethanol would make up the highest concentration. Some water would be found in the mixture because of product overlap and because ethanol and water have similar boiling points. The overhead vapors could be distilled further if needed by sending the overhead to another distillation tower. Methanol and water distillation. Under normal conditions, methanol boils at 148 degrees Fahrenheit or 64.4 degrees Celsius, and water boils at 212 degrees Fahrenheit or 100 degrees Celsius. A 50-50 mixture heated to 180 degrees Fahrenheit or 82 degrees Celsius would start the vaporization process at atmospheric pressure. The vapor concentration would be 80% methanol and 20% water. This incomplete separation is called overlap. The temperature at which this concentration is produced is referred to as the effective cut point. If the mixture were heated to 212 degrees Fahrenheit or 100 degrees Celsius, both methanol and water would vaporize, and a 50-50ths vapor mixture would be obtained. Another viewpoint states that the higher concentration of methanol in the vapor is based on Raoult's law, which states that the partial pressure of component is the product of the vapor pressure and the mole fraction of the component. Kinetic energy. Liquids are composed of molecules that are closer together than the molecules of gases. The speed at which these molecules move is proportional to the amount of heat they encounter. As heat is transferred to a liquid, the molecules begin to speed up and move farther apart and the liquid expands. This molecular motion is referred to as kinetic energy. Its temperature determines the kinetic energy of a liquid. Sensible and latent heat. Distillation involves both vaporization and condensation. The heat that produces state changes consists of sensible and latent heat. Sensible heat can be sensed or measured. Latent heat of vaporization, the heat required to change a liquid to vapor, cannot be sensed or measured. For example, suppose you have a feed tank filled with heptane, which boils at 209 degrees Fahrenheit or 98 degrees Celsius under atmospheric conditions. Before heat is added, the temperature is 72 degrees Fahrenheit or 22 degrees Celsius. As heptane is pumped to a column, it is heated by a shell and tube heat exchanger. As the temperature of heptane rises, the effect of sensible heat can be measured. As the temperature approaches 209 degrees Fahrenheit, the effect of latent heat can be observed. At 209 degrees Fahrenheit or 98 degrees Celsius, the temperature stops rising and a great deal of vapor is produced. Latent heat is thermal energy that has been added to heptane but does not cause the temperature to change. Pressure. Pressure is defined as force or weight per unit area. The term pressure typically is applied to gases or liquids. Pressure is measured in pounds per square inch, psi. Atmospheric pressure is produced by the weight of the atmosphere as it presses down on an object resting on the surface of the Earth. Pressure is directly proportional to height. The higher the atmosphere, gas, or liquid, the greater the pressure. At sea level, atmospheric pressure equals 14.7 psi. Three types of pressure are important to the vaporization process: vapor pressure, control pressure, and vacuum. Vapor pressure is the force exerted as molecules escape the surface of the liquid. In a closed container, the effects of vapor pressure can be observed. As the temperature of a liquid rises, more molecules escape the surface of the liquid, and the vapor pressure rises. The lower the boiling point, the faster the vaporization process occurs. Pressure is measured and controlled at the top of the column. When pressure is added to a liquid, molecules are forced back into solution. More heat is required to vaporize the liquid. This concept is important to understand because having to add pressure in a distillation tower could force you to expend more energy. It can also limit tower efficiency and stop vaporization in severe cases. Boiling point and vapor pressure. The boiling point of a substance is the temperature at which 1. Vapor pressure exceeds atmospheric pressure, 2. Bubbles become visible in the liquid, and 3. Vaporization begins. Molecular motion in vapors produces pressure and increases as temperature is added to the liquid. The vapor pressure of a liquid is a physical property of the liquid at a given temperature, independent of the volume of the liquid. The same no matter what gas or pressure is above it. The same even if a vacuum exists above the liquid. More often associated with closed containers. Measured when the rate of liquefaction is equal to the rate of vaporization, equilibrium. Used to determine the boiling point of a liquid when the temperature and vapor pressure equal atmospheric pressure. The vapor pressure of a substance can be directly linked to the strength of the molecular bonds of a substance. The stronger the bonds, or molecular attraction, the lower the vapor pressure. If a substance has a low vapor pressure, it has a high boiling point. For example, gold changes from a solid to a liquid at 1947 degrees Fahrenheit or 1064 degrees Celsius and boils when the temperature reaches 5084.6 degrees Fahrenheit or 2807 degrees Celsius. Water changes from a solid to a liquid at 32 degrees Fahrenheit or 0 degrees Celsius and boils when the temperature reaches 212 degrees Fahrenheit or 100 degrees Celsius. Liquids do not need to reach their boiling points to begin the process of evaporation. For example, a pan of water placed outside on a hot summer day, 98 degrees Fahrenheit, or 36.6 degrees Celsius, will evaporate over time. The sun increases the molecular activity of the water vapor, and some of the molecules escape into the atmosphere. Wind currents enhance the process of evaporation by sweeping away water molecules, which are replaced by other water molecules. Pressure impact on boiling. Pressure directly affects the boiling point of a substance. As the pressure increases, the boiling point increases, the escape of molecules from the surface of the liquid is reduced proportionally, the gas or vapor molecules are forced closer together, and the vapor above the liquid could be forced back into solution. The effects of pressure are important for a process technician to understand. A change in pressure shifts the boiling points of raw materials and products. Pressure problems are common in industrial manufacturing environments and must be controlled. Vacuum distillation. Vacuum distillation is used commonly by the chemical processing industry. Atmospheric pressure is 14.7 psi, and any pressure below atmospheric is referred to as vacuum. Inside a distillation column, vacuum affects the boiling point of a substance in the opposite way that positive pressure does. Instead of moving molecules closer together, it encourages them to move apart. The effect of vacuum pressure is very helpful in situations in which large, heavy hydrocarbons are being broken down in the bottom of a column. Adding heat can damage equipment and product. Vacuum towers offer an excellent option in situations that normally would require high temperatures. Vacuum systems lower the boiling point of a substance, enhance the molecular escape of molecules from the surface of liquid, reduce energy cost, reduce molecular damage by overheating, and reduce equipment damage. When heat is added to the distillation system, molecular activity increases and vapor pressure increases. Because a distillation column is a series of stills stacked one on top of the other and pressure changes affect the boiling points, each stage must be considered separately in pressure calculations. The following list identifies only a few of the considerations that need to be reviewed for pressure calculations on a tower. The liquid level on each tray puts pressure on the tray. Rising vapors encounter resistance at each plate, which slows them down, creating pressure. Each tray has a different mixture on it. Vapor pressures vary between trays. Inlet feed tray pressure varies if feed composition changes. Flow rate changes affect tower pressure. Downcomer liquid level puts pressure on the plate. Reboiler discharge increases pressure where it enters the tower. Cool reflux slows molecular activity. Each tray has pressure from above, below, and within the stage. Vacuum distillation allows vapor molecules to escape to the surface of the liquid at lower temperatures. Vacuum towers usually are wider than normal towers because of high vaporization rates. Vacuum distillation allows heavier hydrocarbons to be separated without damaging the molecular structure with excessive heat. The use of vacuum conditions will result in decreased temperatures in the tower or column. Vacuum distillation is often used to safely separate azeotropic mixtures. An azeotropic mixture is defined as a mixture of two or more components that boil at similar temperatures and at a certain concentration. The liquid and vapor concentrations of an azeotrope are equal. Other methods used include the addition of an entrainer that will affect the volatility of one of the components. Examples of this can be found in azeotropic distillation, chemical action distillation, dissolved salt distillation, extractive distillation, and pervaporation and other membrane methods. Cryogenic distillation, oxygen and nitrogen. Cryogenic distillation can be used to separate the two major components of the Earth's atmosphere, nitrogen and oxygen. Modern manufacturing utilizes a three-phase approach to this operation: a warm-in section, a cold box, and liquid oxygen or nitrogen storage. Our atmosphere is composed of 78% nitrogen and 21% oxygen. In the cryogenic process, the air in a distillation column is cooled to -173 degrees Celsius or 100 K to produce high-purity nitrogen. Oxygen starts to liquefy at -112 degrees Celsius in the cold box. While similar equipment is used for each of these processes, the system will either be used for nitrogen or oxygen separation. Two figures are included with this section to help a new technician see the various equipment arrangements used for each operation. Oxygen process. During the oxygen cryogenic process, a compressor is used to draw outside air into the warm-in section and transfer it to a receiver. The compressed air generates heat and needs to be passed through a chiller before moving into the coalescing filter section. The final step takes the compressed air and sends it through an activated carbon adsorber. This completes the warm-end process. The equipment used in this section includes a compressor, piping, valves, receiver, chiller, instrumentation, filter, and redundant adsorber drums. The equipment found in the cold box includes heat exchangers, turbines, and a packed distillation column. As air enters the cold box, it flows into the main heat exchanger where it is cooled to -112 degrees Celsius. At this temperature, some of the oxygen liquefies and enters into the boiler where complete liquefaction occurs as the cooled liquid oxygen evaporates. Air leaves the boiler and flows into the top of the packed column where it is allowed to flow down through the packing material, giving up the lighter nitrogen gas. The evaporated oxygen steam from the boiler vents into the lower section of the column where it flows upward and contacts the liquefied descending oxygen. As the liquid oxygen flows downward and through the packing, it becomes richer and richer in oxygen content and is collected at the bottom of the column. From here it can be transferred to the liquid oxygen tank. In the nitrogen cryogenic process, the warm end process is the same. However, upon entering the cold box, the main heat exchanger rapidly cools the air to -165 degrees Celsius. Nitrogen collects in the top of the column while oxygen pools at the bottom. Liquid nitrogen is sent to and stored in a tank. Refrigeration for the oxygen and nitrogen cryogenic process is provided by an air brake expansion turbine physically located at the base of the cold box. High-pressure gas is expanded to low pressure and cooled in the turbine. Gas laws and distillation. A distillation system is by nature designed to separate the components in a mixture. As the mixture is heated in a furnace or heat exchanger, the piping keeps the liquid confined as it expands, artificially shifting the boiling point. The feed rate to the column is carefully controlled. The heated mixture enters the column on the feed tray and rapidly expands, with the lighter components vaporizing and the heavier liquids cascading down the internals of the column until they gain enough heat energy to flash or vaporize. The different trays in the column have unique molecular components associated with volatility. If you know the vapor pressure exerted by a specific chemical, you can calculate its partial pressure on the various trays. To do this, we use Dalton's law of partial pressure, that is P total equals P1 plus P2 plus P3, which states that the total pressure of a gas mixture is the sum of the pressures of the individual gases, that is, the partial pressures. Furthermore, Dalton's law states that the total pressure of a gas mixture is the sum of the pressures of the individual gases or partial pressures. This picture illustrates Dalton's law of partial pressures. To see Dalton's law applied, here are some examples. A mixture of 25% hexane, 50% benzene and 25% heptane will exert a predictable pressure at 175 degrees Fahrenheit. To calculate partial pressures, use the formula. Partial pressure equals vapor pressure times percent of fraction. For example, consider the following data shown in picture. Given the data, the vapor pressure exerted by a mixture consisting of 25% hexane, 25% heptane, and 50% benzene could be calculated as shown in this picture. Using this information, we can calculate the total pressure on tray 6 by adding up the partial pressures. This information also illustrates that the chemical with the highest volatility is hexane, C6H14, which has a boiling point of 69 degrees Celsius or 156.2 degrees Fahrenheit. Heptane has a boiling point of 98 degrees Celsius or 208.4 degrees Fahrenheit. Benzene has a boiling point of 80.1 degrees Celsius or 176.2 degrees Fahrenheit and represents the lowest percentage of the three components in vapor state above the tray. The larger the difference between the partial pressures, the easier it is to separate the fractions by boiling point. The original mixture had a 25% heptane, 25% hexane, and 50% benzene liquid concentration. The larger the difference between partial pressures, the easier it is to separate the fractions by boiling point. Equilibrium curves as shown in picture are used to determine the composition of a vapor above a boiling liquid and how one mixture differs from another. The ideal gas law PV equals nRT calculates the pressure, temperature, volume, or moles of any ideal gas, where P equals pressure of the gas, V equals volume, N equals moles of gas, T equals temperature in Kelvin, K, R equals ideal gas constant, 0.08206 liters times pressure, in atmospheric, per mole times K. The combined gas law is used to calculate changes in a gaseous substance from one condition to another. P1V1 divided by T1 equals P2V2 divided by T2. Ideal and non-ideal systems. Efficient tower operation requires an operator to understand the theory of distillation and the key components of a distillation system. It also requires years of field experience. The distillation theory is related to two types of systems, an ideal, binary or two-component, system and a non-ideal, complex, multi-component, system. Distillation design theory is based on heat and mass transfers from tray to tray. Distillation calculations are used to determine vapor-liquid equilibrium data. A common equation used to determine performance is Raoult's law. K1 equals Yi equals Pi, Xi equals P, where K1 equals equilibrium constant volatile, Yi equals mole fraction in vapor, Xi equals mole fraction in liquid, Pi equals vapor pressure of composition at temperature and P equals total system pressure. Heat balance and material balance. Heat and material balance as shown in picture variables must be understood by a technician to keep a distillation column functioning properly. As the feedstock is gradually heated up from 80 degrees Fahrenheit to operating temperatures, a variety of technical equipment can be used. For example, heat exchangers are frequently used to heat up materials. Typically, the exchangers are set up in series and the temperature is increased. Through the principles of conduction, convection, sensible heat, latent heat, and others, heat transfer occurs. Flow rates measured in gallons per minute are exposed to hot oil or steam that transfer energy through solid walls and into a moving fluid matrix. As these materials enter a distillation column, the pressure of the liquid being released on the feed tray or through the feed distributor immediately gives up heat energy. This heat needs to be sustained and controlled. These pictures show the detailed specifications of a heat exchanger and a preheat system. All raw materials entering a tower are converted into products. Material balance theory states that the sum of the raw materials entering must equal the total of the products leaving the distillation tower. Column loading is another term associated with material balance. It is defined as the amount of material fed continuously into a distillation column. Heat balance states that the heat that goes into a distillation column must be equal to the heat that goes out of it. Maintaining this balance is critical to the proper functioning of the tower. To better understand how the principle of material balance works, let's consider the flow of raw materials through a column. Flow enters the column at 550 gallons per hour. This is roughly equal to 10 barrels per hour. Flow leaves the tower through one of three paths: bottom, side stream, or top. The bottom's product contains heavier molecules than the side stream or top. To obtain the material balance, add the sums of the three outlet flows. This number should equal the sum of the inlet flow. By knowing the boiling points of the different components in the feed mixture, an operator could determine the approximate material composition and the place on the tower each component will exit. Heat balance operates under the same principle as material balance. What goes in must come out and must be maintained in order to hold the heat balance. Initially, tower temperature gradients are established by engineering. The temperature gradient is the temperature profile that exists on the tower from bottom to top. Tower temperature is maintained so the expected separations occur. Temperature in a tower can be affected by pressure, flow rates, fluid levels, feed composition, reflux rate, and equipment problems. Plate columns. Plate columns, sometimes called tray columns, come in three basic designs: bubble cap, sieve, and valve tray. The basic components of a plate column include the feed inlet, feed tray, rectifying or enriching section, stripping section, bottom outlet, overhead outlet, reflux line, reboiler, condenser, feed preheater, side stream outlets, downcomer, weir, riser, control loops, pipes, pumps, valves, instrumentation, and computers as shown in pictures. The tray arrangement inside a plate distillation column will depend on the specific process for which it is being used. The tray in picture has all three types of components. Bubble cap trays are used commonly in the distillation process. As liquid vaporizes in a bubble cap column, it has to pass through individual trays. A tray has many bubble caps mounted on a riser, covered by liquid. As the vapor pressure increases from the bottom of the tower, the bubble caps lift and allow a small amount of vapor through. Slots notched into the side of the cap enhance vapor and liquid contact as shown in picture. This vapor comes into direct contact with the liquid on the tray and transfers some heat energy. The liquid condenses the heavier components of the vapor, whereas the lighter components move up the tower. A wear on the tray maintains a liquid level over the caps. As heavier condensate builds up, it flows over the weir and out a device called a downcomer. The downcomer discharges onto the tray under it. Sieve trays, as shown in picture, the simplest type of tray. A sieve tray is essentially a metal plate with small holes in it. The holes range from 1 inch to 1/8 inch in diameter. As vapor comes through the holes, it moves too fast to be stopped by the liquid level on the tray, but it does slow down significantly as it passes through the liquid. The pressure drop through a large number of small holes is greater than the drop through fewer large holes. This information is important for controlling pressure. Valve trays, as shown in picture, have simple, movable plates. Plate movement depends on process flow. This type of tray is more efficient over a wider range of flow rates than the sieve tray. Each valve is a metal strip or a small metal disc that lifts under vapor pressure. Flow is directed horizontally on the tray to produce good mixing. Inlets and outlets. The feed inlets are located between the rectifying and stripping sections. Distillation columns can have 3 or more feed lines. The bottom's outlet is used to remove residue from the distillation column and to feed the reboiler. The overhead outlet is the vapor exit point from the distillation column. The overhead outlet allows hot vapors to pass into the condenser. Feed tray. The location of the feed tray is determined by the ratio of stages above and below the inlet feed line. The ideal feed tray location can fluctuate, so 3 or more feed lines typically are established on a tower. Experimentation identifies which feed point is the most effective. Thermal condition is defined as the amount of heat required to vaporize 1 mole of feedstock, divided by the latent heat of vaporization. If the feed composition changes, the thermal condition of the feedstock will be changed. The composition and condition of the feedstock as it enters the tower affect the number of trays needed, reflux rate, level, pressure, and temperature. Rectifying or enriching section. A tower's rectifying or enriching section is located above the feed tray. Rectification is the separation of different substances from a solution by use of a fractionating tower. As a mixture is heated, the vapors rise through the column. Chemicals that boil first are in the top fraction, those that boil last stay in the bottom fraction. The rectifying section of a tower has a higher concentration of light components than the stripping section has, so it is said to be enriched. Stripping section. The stripping section is located below the feed tray. Feed from the feed tray flows down the tower, stripping the heavier hydrocarbons from the vapor. As the cooler feed drops from the feed tray to the lower trays, it heats up and strips the lighter components. The heavier components flow to the bottom of the tower. Because the trays get progressively hotter as the liquid flows down the tower, lighter hydrocarbons are stripped off the heavier molecules. This process creates a countercurrent movement within the tower as vapor moves up and liquid moves down. The lighter components are vaporized and move up the tower. Temperatures in the stripping section are usually much higher than in the rectifying section. Reboiler or steam injection. Reboilers help control overlap and heat balance. Several types and arrangements of reboilers can be used on a distillation column as shown in picture. Kettle reboilers draw feed from the bottom section of the column by gravity flow. An internal weir holds a liquid level over a heated tubular bundle. A vapor disengaging space above the tubular bundle allows the liquid to boil and roll freely and enrich the void with vapors. As the lighter components break free from the larger, heavier molecules, they rise into the vapor disengaging area and exit the top of the reboiler. A vapor inlet port is located below the bottom tray or packing support. An important criterion for a distillation column is that any heat energy lost must be returned. Reboilers are used to restore heat balance and add additional heat for the separation processes. Bottoms products typically contain the heavier components from the column. Reboilers suction off the bottoms product and pump it through their system. Product flow enters the bottom shell side of a reboiler. As flow enters the reboiler, it comes into contact with the tubular bundle. The tube bundle typically has steam flowing through it. As the bottoms product comes into contact with the tubes, a portion of the liquid is flashed off and captured in the dome-shaped vapor cavity at the top of the reboiler shell. This vapor is sent back to the tower for further separation. A weir contains the unflashed portion of the liquid on a reboiler. Excess flow goes over the weir and is recirculated through the system. A thermosiphon reboiler is a fixed-head, single-pass heat exchanger hooked up on the side of a tower to add additional heat to the process. One side of the exchanger is used for heating, usually with steam, the other side takes suction off the tower. Thermosiphon reboilers come in vertical or horizontal designs. The lower leg of the exchanger usually takes suction at a point low enough on the tower to provide a liquid level to the exchanger. A pump is not connected to the tower and exchanger. This system uses buoyancy forces to flash off and pull in liquid. As vapors are flashed off into the tower, the suction line draws in an equal amount. Overhead condenser. Condensers are typically tube and shell heat exchangers used to condense hot vapors into liquid. A condenser can be found at the top of most distillation columns as shown in picture. A heat exchanger that is used to convert the entire overhead vapor to liquid is called a total condenser. This type of condenser is designed to split the distillate into two streams. As vapor flow leaves the column, it enters the overhead condenser, comes into contact with a much cooler environment, and condenses. The condensed liquid collects in an accumulator or drum. A pump takes suction off the accumulator and directs flow to two locations. The primary stream moves the distillate to the product tanks or on for further processing. The secondary stream is pumped back into the column as reflux. Partial condensers are designed to return all of the condensed liquid back to the top tray of the tower and to function as an external top tray for the tower. Partial condensers also convert 50% of the overhead vapor to distillate and separate vapor from the accumulator, sending it on for further processing. A shell and tube heat exchanger is mounted at the top of a distillation column. Hot vapors pass over chilled tubes and condense. The condensed vapors are collected in an accumulator or receiver. Some columns use the same technique to cool side stream draws off a tower. Reflux line. Distillation columns do not always work perfectly. Overhead, side stream, and bottoms products usually have some composition overlap. Overlap can be controlled or limited by returning part of the overhead product to the tower. This process is referred to as refluxing, and the returned product is called reflux. Cooled reflux keeps a liquid level on the upper trays and condenses heavier molecules. Each component of a mixture pumped to a column has a unique boiling point. The upper rectifying trays, middle feed tray, and lower stripping trays have different temperatures and different products on them. The principle of total reflux exists in a distillation system when the overhead vapors are condensed and returned to the top tray inside the column. When a distillation column is placed on total reflux, feed to the column is stopped, bottom and side stream flows are stopped, and the overhead product is condensed and returned to the column as reflux. This type of operation is commonly used to test the tower or to put the system in standby. It is easier and cheaper to run the tower on total reflux than to shut it down and then restart it. Downcomers and risers. Downcomers are directional devices integrated into the tray design to funnel liquid from upper trays to lower trays in a distillation column. Risers are located on the plates. In some systems, they appear to be tubes that allow hot vapors to flow between trays. The top of the riser usually has a bubble cap or valve attached. Because bubble caps and valve trays come in over 30 designs, the riser also can be associated with the lower leg of the device that rises and allows vapor to flow up. Feed preheater. The feed preheater is usually a shell and tube heat exchanger or a fired furnace. Fired furnaces or reboilers provide the initial heat to a distillation column's feed. Heating the feed avoids thermal shock and matches the temperature set point of the feed tray. Temperature controls are tied to the operation of the feed preheater. In most cases, the flow usually is adjusted to the feed, or in some cases the preheater's steam rate is regulated. Side stream outlets. A side stream can be located on every tray or stage of a column. Liquid or liquid vapor mixtures are removed and cooled in a condenser. The cooled liquid collects in an accumulator or receiver and is pumped to a separate product tank. Pressure, temperature, level, and flow indicators. Pressure gauges are used to provide valuable information about conditions inside a distillation column. Thermocouples are used to sense temperature changes on a process unit. Level control systems are used to maintain levels in 3 or more systems. Flow controllers are used to maintain flow rates in and out of the column. Differential pressure between trays or column sections is an important indicator of load and flooding conditions. Control loops. The basic elements of a control loop include primary elements and sensors, a transmitter, a controller, a converter, and a final control element. Control loops are used by process technicians to automatically control some of the process variables found in a distillation system. The most common variables controlled by this type of automation are flow, temperature, level, pressure, and composition. A level control system monitors the level in the bottom of the tower. Part of the stream is sent to a reboiler and part is sent onto a product tank. Level control systems use a sensing device, transmitter, controller, and control valve. This same system exists on the overhead accumulator, the side stream accumulators, and the feed systems. A temperature control system monitors tower temperatures and adjusts flow through the reboiler and preheater. As temperature drops in the tower, more feed is allowed into the reboiler. The reboiler is a critical part of the heat balance system. This device returns heat to the tower by flashing some of the liquid into vapor and returning it. Distributed control system. The distributed control system is a computer-automated system used to operate process equipment from remote locations. Packed columns. Packed distillation columns provide a unique approach to vapor-liquid or liquid-liquid contact during the distillation process. Packed towers use specially designed packing materials to provide more surface area for maximum contact between gases and liquids. Liquids wet the surface of the packing as they migrate down the tower. Rising vapors come into contact with the wetted surface and exchange heat. In many packed distillation columns, hot vapors and liquids compete for access through the same points. As they do in any distillation process, lighter components move up the column while heavier ones move down. In a packed column, liquid travels down through feed distributors, hold-down grids, random and structured packing, support plates, redistributors, liquid collectors, structured grids, and finally into the bottom section as shown in picture. Hot vapors move countercurrent to the downward flow of liquid. There are 3 types of packed distillation columns: random, structured, and stacked. Random packing includes discrete pieces of packing that are randomly dumped or poured into a packed column. Packing provides a surface for good vapor-liquid contact, distillation efficiency characteristics, and predictable pressure drop. Structured packing has specific geometric shapes, like a mesh. It works best in columns requiring high liquid loadings. Stacked packing is uniformly arranged inside a distillation column. Packed columns are designed for pressure drops between 0.20 and 0.60 inch of water per foot of packing medium. Shell. The cylindrical shell of the distillation column is typically metal, carbon steel, stainless steel, special alloy, or non-ferrous. Columns can also be composed of glass, ceramic, plastic, or wood. The type of chemicals that will be used in the distillation column will determine the design material, lining specification, wall thickness, pressure rating, and temperature rating. The inside shell of some packed distillation columns is lined with brick and a special heat and acid-resistant mortar. Packing. The packing used in a distillation column provides the heart of the operation. Inside a distillation column, packing is either random or structured. Typically, a combination of both is used in a packed column. Random packing may be dumped into a section of the column or carefully stacked. The random spacing of the packing or areas between the packing gives this section its name. Structured packing comes in preformed layers that overlap into a single unit. The uniform spacing between voids characterizes the functionality of this section. Packing comes in a variety of designs and sizes as shown in picture. Some of these designs are burl saddle, interlock saddles, rasking ring, cross-partition ring, flexi ring, spiral ring, mini ring, and Sulzer packing. A variety of other packing designs can be found in the chemical processing industry, but these are the most popular. As hot feed is injected into a packed distillation column system through the liquid distributor, it encounters a rapid pressure drop. This pressure drop allows a percentage of the feed to vaporize while the rest of the liquid fraction is evenly distributed over the packing. Heat balance inside the packed column is maintained with one or more of the following systems. Kettle or thermosiphon reboiler system. Direct injection of steam. Electric heaters on the column. Steam tracing on the column. Furnace system. A kettle reboiler is a device designed to add heat to the column. Kettle reboilers take suction off the bottom of the column and heat it up until a part of it vaporizes and is sent back to the column. The liquid that does not vaporize is sent to another system for further processing. A thermosiphon reboiler is a vertical, shell and tube heat exchanger mounted near the bottom of the column. Steam is used to reheat the bottom product. A series of electric plate heaters can be used to heat a packed distillation column. Electric heaters are typically used in small systems that are enclosed in buildings. Another design that does not require environmental protection is steam tracing. Steam tracing uses copper tubing that can easily be wrapped around the outside of a distillation column and insulated. As steam passes through the tubing, heat energy is transferred by conduction into the column. Insulation holds much of the heat in and protects the column from the elements. A furnace system may be used in large commercial operations where bottom feed is circulated into a small furnace and back to the column. Furnace systems provide large-scale temperature control where flow rates into the column are high. Steam can be injected directly into the bottom of a packed column to heat up the process. Open, or direct, injection allows 100% conversion of TUS into the liquid and helps reduce effective partial pressures of different components. Open injection replaces the need for a reboiler. In a binary system, a system with two components, where the major component is water, open or direct injection of steam is a suitable alternative to using a reboiler. Packing supports. The packing inside a distillation column is supported by packing supports. These devices come in a variety of shapes and designs as shown in picture. Each support is engineered to hold up the combined weight of the packing and liquid under a variety of abnormal conditions. Some of these conditions include pressure surges, localized flooding, and temperature and flow variations. Packing supports are designed to provide sufficient air-liquid passage and to prevent the packing from migrating into the lower sections of the column. Packing support plates come in the following designs: flat sieve plates, gas injection support plates, grid supports, cone supports, and corrugated supports. Bed limiters and hold-down plates. Bed limiters and hold-down plates as shown in picture are engineered to keep fixed bed packing from migrating or fluidizing out of the section. Hold-down plates rest on top of the packing, whereas bed limiters are attached to the inside wall of the column. Hold-down plates are primarily used on carbon and ceramic packing. Bed limiters are used on metal or plastic packing. During normal operations, a packed column will experience minor fluctuations in the packing. Depending on the relative volatility of the various components found in a chemical mixture, the packed column can experience significant pressure differential across the upper and lower sections. It is possible for a packed column to experience local and overall flooding as the voids between the packing and stages fill up. Flooding causes severe pressure differences between sections in the column. Bed limiters and hold-down plates keep the internal components of the column stable and in operating condition. Vertical packed column. An important part of engineering design is the vertical slant of the column. Most columns are never straight up and down. Shifting of the tower's alignment, which can be caused by soil movement, wind sway, poor foundation construction, or uneven thermal expansion, can severely decrease efficiency in the column. Liquids in a column will flow toward the downward sloping end of the packed section. This phenomenon, referred to as channeling, will cause uneven distribution of the wetting process and will unbalance the internal vapor-liquid flow. Vapors flow faster through dry sections of packing and slower through the wetted parts. Pilot tests of random packed columns placed on an incline identified efficiency reductions of 5% to 10% for each degree of inclination. In severe cases, 25% to 50% decreases in efficiency have been noted for each degree of inclination. Structured packing provides a more stable efficiency environment with recommended tolerances between 0.2 degrees and 0.5 degrees. Liquid distribution and redistribution. Packed distillation columns use liquid distributors to disperse fluid evenly over the top of the packing. This process plays an important role in the efficient operation of the column. Poor liquid distribution reduces vapor-liquid contact and promotes channeling. Common liquid distributor designs are ladder pipe, spray distributor, perforated ring distributor, notch trough distributor, tunnel orifice distributor, rear riser distributor, and orifice pan distributor as shown in picture. In most packed columns, the downward flow of liquid is occasionally redistributed. This process tends to pull the liquid off the walls and redirect it into the center. Plate distillation system. This section describes a typical plate distillation system, which involves several subsystems. The primary subsystems are the feed system, the preheat system, the distillation column, the overhead system, and the bottom system. All of these systems work together to produce products that meet or exceed customer specifications. Feed system. A collection of product storage tanks is often referred to as a tank farm. The tank farm has a complex system of piping, valves, and pumps that allow the technician to line up the various tanks in a number of arrangements. The tank farm in this example has 4 storage tanks assigned to the debutanizer distillation column as shown in picture. The primary feedstock used for this distillation process is a binary mixture of 37% butane and 63% pentane. Tank 702 receives feed from a sister unit on the west side of the chemical plant complex. At the base of TK702 are 2 centrifugal pumps that transfer feed to the preheat section and to the distillation column, C702. During startup, the off-spec tank 720 is used to store product that does not meet customer specifications. The bottom and overhead lines are lined up into the off-spec system during startup. This mixture can be fed back into the system, or it can be used as a feedstock for a sister unit. A level indicator provides a readout inside the control room for TK702. High and low level alarms support the level control system. A flow control loop, FIC702, is used to regulate the flow of product to the unit. Flow rates are slowly increased in 50 GPM increments, up to 200 GPM. Only one pump at a time is used to transfer feed to C702. A product analyzer keeps a close eye on the uniformity of the feedstock. Each minute pump P702 operates, 74 gallons of butane and 126 gallons of pentane are sent to distillation column 702. Preheat system. The preheat system is shown in picture uses two horizontal shell and tube heat exchangers to heat the butane-pentane mixture, X702 and X703. Each exchanger has a shell inlet and outlet and a tube inlet and outlet. The butane-pentane mixture flows through the shell side of each exchanger. X702 and 703 are set up in series flow. A flow control loop, FIC702, regulates fluid flow into the column. During operation, feed flows through the system at 200 GPM. The butane-pentane mixture enters X702 at between 70 degrees and 80 degrees Fahrenheit and exits at 120 degrees Fahrenheit. Feed temperature enters X703 at 120 degrees Fahrenheit and exits at 180 degrees Fahrenheit. A low-pressure steam system is used as the heating medium for the tube side of X703. A thermocouple is located on the inlet feed line to the column. Steam flow to X703 is controlled at 180 degrees Fahrenheit with TIC 701. The hot pentane flowing from the bottom of C702 is used as the heating medium for X702. This process allows heat to be transferred from the pentane to the butane-pentane feedstock mixture. Correct valve lineup into and out of the exchangers is an important feature of operating the preheat system. A product analyzer continuously monitors feed composition. Distillation column. The basic components of the distillation process include the column, the preheaters, pumps, the condenser and drum, and the reboiler. A 10 psi nitrogen blanket is kept on the unit while the system is down. The central piece of equipment in distillation is the column as shown in picture. During startup, cold feed is sent to the column at 50 GPM to allow the steam heating systems to be engaged. As cold feed enters the column, it drops from the feed tray to the bottom of the column. The bottom outlet line feeds a kettle reboiler located at the base of the column. As the level rises in the column, it simultaneously rises in the reboiler. Steam flow is open to the tube side of the kettle reboiler X705. As the temperature starts to increase, the flow rate is increased in 50 GPM increments up to 200 GPM on FIC702. As the butane-pentane mixture heats up, butane vapors begin to rise up the column. As the vapors rise and cool off, liquid begins to accumulate on each tray. As more heat is absorbed, a higher concentration of pentane vapors moves up the column with the butane, but it will primarily concentrate in the stripping section below the feed tray. Only about 2% to 5% of pentane will overlap with butane. A temperature gradient, 222 degrees Fahrenheit bottom to 159 degrees Fahrenheit top, begins to form across the various plates in the column. Higher temperatures will concentrate in the bottom of the column and lower temperatures near the top. A level control system holds a constant level in the bottom of the column. When the column first starts operating, product purity will be off specification. This process will continue until each set point and process variable matches unit specifications. The overhead system is designed to cool and trap the overhead vapors. Overhead system. The basic components of the overhead system are the top of the column, the overhead condenser, X704, a drum, D702, two pumps, P709A and P709B, and a series of control loops as shown in picture. As hot butane vapors leave the top of the column, the overhead condenser partially condenses the vapors. Flow control loop FIC703 automatically maintains 420 GPM cooling water to condenser X704. Liquids are easier to transfer than vapors. A 50% level is typically maintained on D702 by LIC703. Pump 709 transfers feed from D702 to the tank farm, TK710, or back to the top of the column as reflux. reflux rates are maintained at 130 GPM, while product to TK710 flows at around 74 GPM. An analyzer monitors reflux product purity to keep it at 98%. A temperature control loop, TIC703, is cascaded to the reflux flow control loop FIC705 to control the top temperature at 159 degrees Fahrenheit. During operation, the flow control loop on the reflux line can operate independently. However, controlling the temperature is more important than controlling the flow rate. In this type of system, a cascade temperature loop can be established, which allows a thermocouple, transmitter, and controller to act as the primary or master controller for FIC750. In this example, FIC705 and all 5 elements of the control loop act as the final control element for TIC703. 74 gallons per minute of 98% butane is sent to TK710 in the tank farm. A pressure control loop, PIC702, regulates the pressure on the overhead system at 100 psi. Some minor butane loss occurs through this system. Excess vapors are directed into a flare header system. Bottom system. Temperatures in the bottom of C702 are controlled at 222 degrees Fahrenheit. A kettle reboiler, X705, utilizes a natural circulation feed system as shown in picture. Gravity flow provides a constant level to the reboiler, where levels are held at 50% by LIC702. This level allows the upper 2 tubes in the reboiler to be exposed above the liquid level to ensure good vapor return to the column. LIC702 allows the 92% hot pentane to flow to X702 and then to TK730 in the tank farm. Bottom flow rates are around 126 GPM. Correct lineups are important from the bottom of the column to the tank farm. FIC700 controls steam flow rates to the kettle reboiler. TIC702 has a thermocouple and transmitter mounted above the reboiler vapor inlet line on the bottom of the column. During line-out conditions, TIC702 operates as the primary or master controller for FIC700. An analyzer monitors the composition of the pentane bottoms product. Troubleshooting a distillation system. Process technicians troubleshoot process systems in a variety of ways. One of the more common methods of troubleshooting is to check the difference between the set point and the process variable. In Picture A, the system is operating correctly. The process variable and set point match exactly. A process upset in progress can be identified in Picture B. The set point is 30%, but the process variable is 26%. The difference could be a result of instrument error, pump problems, low bottoms level, or valve problems. In Picture C, a full-scale process upset is occurring. The initial problem was the partial failure of the steam valve, TIC2. Look at the other process variables affected by the higher bottom temperature on the column. Problems in a distillation column typically include feed composition changes, puking, flooding, and equipment or instrumentation failure. The feed has a specific composition. It may be a binary or ternary mixture. It must be controlled to ensure a uniform operation. Puking is a problem that can upset trays, push products up or down the column or out the overhead line. Equipment or instrumentation failure can also damage the operation of a distillation column. Temperature, flows, pressure, level, and composition variables are closely tracked. Other problems include flooding, which will result in liquid accumulation in the tower, increased pressure drop, and poor separation of components. Other problems include downcomer flooding, jet flooding, local flooding, weeping, and overloading. Downcomer flooding occurs when the liquid flow rate in the tower is so great that liquid backs up in the downcomer and overflows to the upper tray. Liquid accumulates in the tower, differential pressure increases, and product separation is reduced. Jet flooding occurs when the vapor velocity is so high that liquid downflow in the tower is restricted. Liquid accumulates in the tower, differential pressure increases, and product separation is reduced. Local flooding is when excessive liquid flowing down a column blocks vapor flow up the column in one section. Technicians will typically break a flood by decreasing the feed rate, the reflux rate, or the bottom temperature. Overloading is best described as operating a column at maximum conditions. Weeping is a phenomenon that occurs when the vapor velocity is too low to prevent liquid from flowing through the holes in the tray instead of across the tray. Differential pressure is reduced, and product separation is reduced. Another concept that occurs in distillation is the temperature at which the feed first boils, or initial boiling point, versus the final boiling point of the heaviest components. Final boiling point is the temperature at which the heaviest component boils. Starting up a distillation system. Operating the distillation system requires teamwork and a good understanding of equipment and technology. Each unit has a standard operating procedure, SOP, that provides a systematic approach to unit startup. These procedures are not merely suggestions, rather, they are requirements associated with the job. The team that will start up a unit will typically include an inside and an outside operator. Maintenance and engineering support are always close by. In all situations, safety is always considered first, and any potential hazard is addressed prior to the startup. A distillation system is not designed to be started up in 5 minutes and producing prime product 10 minutes later. Typically, the process is started up systematically in a sequential, step-by-step process that requires attention to detail and quick reactions when necessary. The following procedure is intentionally simplistic and designed to show the basic elements of a startup. These 4 pictures illustrate a simplistic distillation system that the following procedure is attached to. Follow the following steps for the startup of the distillation unit. 1. Notify your supervisor and all concerned i.e., engineering, maintenance, etc. 2. Ensure all safety hazards are secured. Trash, locks, old permits, etc. 3. Check equipment and instrumentation. Stroke control valves 0 to 100%, check lineups, etc. 4. Sample feedstock. 5. Line up feed tank to heat exchangers and column. Check each valve lineup. 6. Set feed tank level control to 50%, put in auto. Open feedstock valve to feed tank. 7. Set the overhead, bottoms, and off-spec tanks to 50% and place in auto. Line up dash plus off-spec tank. Column bottoms and top. 8. Line up unit feed pump and both exchangers. Shell side first, then tube side. 9. Set unit feed FIC to required set point. Most units will increase feed in 50 GPM increments. 10. Set hot oil TIC to required set point. Monitor hot oil flow rate and temperature trends. 11. Set kettle reboiler to 50% and put in auto. 12. Line up kettle reboiler bottoms pump to tank farm. Check valve lineup. 13. Set kettle reboiler TIC to required set point, auto. The TIC is cascaded to the FIC. 14. Set kettle reboiler FIC to required set point, auto. Put in CASC shortly after unit startup and feed is flowing. 15. Set unit pressure at required set point, auto. Monitor pressure during startup. 16. Line up reflux pump to column and off-spec, check suction and discharge. 17. Set overhead accumulator LIC to 50%, auto. Watch level increase during startup. 18. Set reflux FIC to required set point. 19. Line up cooling water and set FIC to required set point. Check suction and discharge lineups. 20. Start unit feed pump. Watch levels in accumulator and reboiler. 21. Cascade kettle reboiler steam FIC to TIC. 22. Start bottom and overhead pumps. Do not start without a level. 23. Line up and start off-spec tank pump. 24. Heat catch sample on overhead and bottom product. Take samples to lab. 25. Watch online analyzers for top and bottom purity. Put online when good sample comes back from lab. The following information is a typical example of all of the data, process variables, and so forth recorded, collected, or observed by a process technician. Flow, analytical, pressure, temperature, level, reflux ratio. Reflux ratio is best described as the amount of reflux returned to the tower divided by the amount of overhead product sent to storage. Picture illustrates how reflux is applied to a distillation system. For example, a reflux flow of 128 GPM divided by 64 GPM overhead product being sent to storage equals 2:1 reflux ratio. Reflux is used to control both temperature in the rectifying section and product purity. As hot vapors exit the top of the column, a condenser is used to partially or totally condense the vapors. The level in the overhead accumulator is automatically controlled at 50%. The accumulator in picture has a 9-foot diameter and is 30 feet long. The condenser is designed to condense most of the vapor, however, some is used to control system pressure in the vapor cavity above the liquid in the accumulator. This pressure control process literally backs up and controls all of the pressure on each tray in the column, top tray to bottom. The system pressure in the accumulator and the liquid feed temperature, combined with the liquid height above the reflux pump, provide adequate pressure to the suction side of the pump. The reflux pump is designed to discharge product to storage and to the top tray of the column. One control valve is mounted on the reflux line and another on the product storage line. Frequently, the reflux flow controller is cascaded to a master temperature controller at the top of the column. The reflux rate and cooling water flow rate to the condenser can significantly impact product purity and temperature. Reflux ratios will vary between different applications and are carefully calculated before the first pump or pipe is installed. It is important for a technician to understand the complex relationship the reflux ratio provides to a successful operation. Other problems encountered in column operation. Other problems associated with distillation column operation include entrainment, foaming, and dry tray. Entrainment is best described as the upward movement of high-velocity, large vapor droplets inside a distillation column. Foaming is the result of too much heat, impurities in the feed, or active turbulence on the trays above undersized downcomers. Tray drying occurs when feed rates to the column are low, when reflux rates are low, or when high upward vapor flow rapidly moves from tray to tray. Distillation separates the basic components or fractions of a mixture by their individual boiling points. During the distillation process, a mixture is heated until it vaporizes, then is recondensed on the trays or at various stages of the column, where it is drawn off and collected in a variety of overhead, side stream, and bottom receivers. The condensed liquid is referred to as the distillate. The liquid that does not vaporize in a column is called the residue. A distillation tower can be compared to a series of stills placed one on top of the other. As vaporization occurs, the lighter components of the mixture move up the tower and are distributed on the various trays. The lightest component goes out the top of the tower in a vapor state and is passed over the cooling coils of a shell and tube condenser. As the hot vapor comes in contact with the coils, it condenses and is collected in the overhead accumulator. Part of this product is sent to storage while the rest is returned to the tower as reflux. A reboiler maintains the heat balance on the tower by reboiling the components that have given up some of their energy during the distillation process. A kettle reboiler or thermosiphon reboiler is typically connected to the bottom of the tower. However, reboilers can be attached to the various side streams on the column. A kettle reboiler has a special vapor disengaging cavity that is designed to remove the lighter components from the mixture and return them in the form of heat back into the column below the lower tray. Heavier components in the liquid flow over the weir in the kettle reboiler and out of the tower system. In contrast, a thermosiphon reboiler will vaporize the liquid and return it to the tower operation. Equilibrium curves are used to determine the vapor composition above a boiling liquid and how one mixture differs from another. The larger the difference between boiling points, the easier it is to separate the fractions by boiling point. The temperature in a tower can be affected by pressure, flow, level, feed composition, reflux rate, and upset trays. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.